So we're gonna continue with chapter 15. The chapter 15 homework is gonna be due after spring break, on the 14th. The chapter 15 quiz will be online, the week after spring break from 3/11 through 3/18. Much like the chapter 23 quiz was. And your test grades will be posted to Blackboard by tonight. Probably well before tonight, actually, because they're graded. I just haven't put them on Blackboard yet. I had a couple things I needed to check over before I put them up on Blackboard, that's all. And if you have the last lab on volcanic rocks, you can turn it in. We'll take it. Let's see, that's all I have announcements wise. So, continuing on with chapter 15. We were discussing latitude and longitude. Latitude is the angular measurement in degrees north and south of the equator. It's measured from the center of the Earth relative to the equator. The lines of equal latitude are slices through the Earth parallel to the equator. So there's circles drawn on the surface that are parallel to the equator. This is why lines of latitude are called parallel. Yeah. So lines of latitude are also called parallels. They go from, the values vary from 0 to 90 degrees, north or south. So they go from 90 degrees south up to 90 degrees north. And the poles are at 90 degrees north and south, and the equator is at 0 degrees. So, and the circles of the lines of latitude get progressively smaller as you get closer to the poles. And if you look at the point on the opposite side of the Earth from you, it will have the same latitude number, but the opposite direction. So if you're at 40% degrees north, the opposite side will be at 40 degrees south. Longitude is the other direction. It measures east and west. Lines of longitude are lines from the one pole to the other, perpendicular to the equator. They're also called meridians. They're halves of great circles. They all meet at the poles. And they're measured from an arbitrary location called the prime meridian. It's degrees east or west of the reference meridian, which is the prime meridian in Greenwich, England, which was chosen in a big conference, basically. Because I think it was in the 1880s or so, they decided, everyone got together and decided to choose a meridian for everyone internationally to agree on, because there were several different competing systems. And the one based off with the prime meridian in Greenwich won, mainly because the US and England used it and they were more powerful than the big competitor, which was the French one, which ran through Paris. So if you're at a spot on the Earth where the longitude is 80 west, so the maximum value of the longitude is 180 degrees east or west, and 180 degrees east and west is in fact the same location. Now, to find the spot opposite, it's a little more complicated than it is for latitude, but you first subtract your current value from 180, and then you switch the direction. So if you were at a place where the longitude was 80 degrees west, the other side of the Earth, you'd be at 100 degrees east, which is 180 degrees minus 80. It leaves you with 100, and that will be 80 degrees west. And that's because, this, you can see here, we're measuring from 0. You go to the point opposite, this angle is the same. This would also be 77 degrees. So the angle you're interested in is going to be 180 minus 77, which is 103. So again, you're measuring from 0. So that's how you find the point opposite you in longitude. Another thing we developed are time zones. Time zones, there's 24 time zones. They start at the 0 time zone, which is centered on prime meridian. And their centers are every 15 degrees, roughly. However, they've all been modified for political reasons, so they zigzag all over the place. So for example, if it's 6 a.m. on March 21st in Los Angeles, as you go east, you add time. So you go from -8, you want to figure out what it is in Perth, Australia, to +8. From -8 to +8 is +16 time zones. And so you'll increase the time by 16 hours. So 6 a.m. plus 16 gives you 22, which would come out to 10 p.m. And here's a short video about time zones and the international date line, which is what we use to resolve the fact that, if you keep going in one direction around, you start picking up days. So there's a point where you jump back a day.
In the old days, each town would keep their own times, with a town clock being set to noon when the sun reached its highest point in the sky. However, by the late 19th century, rail had begun to move people across great distances. Schedules became very confusing, as each stop was based on a different town's time. Thus, a need emerged to standardize time so rail could operate more efficiently
and safely. There was the possibility of trains crashing into each other because of confusing time zones. So they developed basically railroad.
In 1884, delegates from 26 countries met in Washington, D.C. to agree on a prime meridian as a common 0 point for longitude. The result was Greenwich, England, being selected as the international standard for 0 degrees longitude and established the 24 time zones. Today, most countries follow the hourly deviations, though they do not always align with longitudes for reasons such as keeping the entire country in one time zone or altering times at certain times of the year, for example, daylight savings time. Time zones are based on the fact that the Earth moves 15 degrees longitude each hour. Since there are 24 hours in a day, there are 24 standard time zones. Time zones are counted from the prime meridian, which is 0 degrees longitude. Each time zone is counted at 15-degree intervals and extends 7.5 degrees either side of the central meridian. For example, Sydney, Australia, lies in the 150 degrees east central meridian, and the time zone includes all locations between 142.5 degrees east and 157.5 degrees east. Now, I will show you how to calculate time zones. First, determine whether the time zone is in the eastern or western hemisphere. If the time zone is east of the prime meridian, such as Australia, it will be at an earlier time than Greenwich Mean Time, or GMT. If it is west of the prime meridian, such as Canada, it will be a later time. Second, count how many time zones away from Greenwich the location is. For example, Greenland is one time zone to the west of Greenwich, so I will subtract 1 hour from GMT to determine the time there. Oslo in Norway is one time zone to the east of Greenwich, so I will add just 1 hour to the current Greenwich Mean Time. When counting the number of time zones away a location is, count the time zone your location is in, but do not count the time zone that Greenwich is in. For example, I will count for Buenos Aires, Argentina. 1, 2, 3, 4. So, if the time is 4:34 GMT, I will subtract 4 hours to find out the time for Buenos Aires. The time will be 0:34. The international date line is an imaginary line lying 180 degrees in the line of longitude, on the opposite side of the Earth to the prime meridian. This line separates one calendar day from another. The international date line deviates in places to avoid crossing any land. In 1994, Kiribati shifted the date line 2,000 miles east to keep the entire country in the eastern hemisphere. In 2011, Samoa and Tokelau skipped a day and moved westward to be in the eastern hemisphere so they could have the same date as Australia and New Zealand, their main trading partners.
So the other way you could do this, which is the example given here, is you can go the other way around. So again, you start in Los Angeles. Go 1, 2, 3, 4, 5, 6, 7, 8 time zones east. Therefore, you'd be 8 hours earlier at 10 p.m. But you've crossed the international date line. So by going 8 hours earlier, it would be March 20th, but you crossed the international date line going east, so you have to increase a day. So it would be, again, March 21st. Now, turns out there are ways you can determine latitude and longitude. So during the year, the sun will appear to change its overhead position, like where on the Earth it's directly overhead, from 23.5 degrees north to 23.5 degrees south. This is because the Earth is tilted 23.5 degrees, and as it orbits the sun, in the summer, in the northern hemisphere, that's when the northern hemisphere is pointing towards the sun. The tilt is pointed towards the sun. At the northern hemisphere, in the winter, that's when the northern hemisphere is pointed away from the sun. That's why also the days are longer in the summer, because the sun is higher in the sky, and shorter in the winter because the sun is lower in the sky and it's in the sky for less time. So the relevant lines that indicate the furthest north and south that the sun can be directly overhead are called the tropics. The northern one is the Tropic of Cancer. The southern one is the Tropic of Capricorn. So anywhere between the Tropic of Cancer and the Tropic of Capricorn, there is at least one day a year, usually 2, that the sun will be directly overhead at noon. And as the Earth revolves around the sun, the noon sun is directly over different latitudes during the year because of the tilt of the Earth by 23.5 degrees with respect to the sun. That is what causes the season, the tilt of the Earth. So the sun in the summer the sun is over the northern hemisphere, so the northern hemisphere gets more sun and is warmer. In the winter, the sun is over the southern hemisphere, so the northern hemisphere gets less sun and it's colder. Mostly has to do with the angle of the light from the sun, but that is what causes the seasons. And this is how the latitude of the sun varies over the year. So it's the furthest north at the summer solstice, June 21st, and the furthest south, the winter solstice, June 22nd. And it's exactly on the equator at the equinoxes, March 21st and September 22nd. At 12 noon, local time, but not necessarily at 12 noon according to your watch, especially here because we're at the edge of a time zone, so we're not actually very close to the line that the time zone is based off of. But at 12 noon, the sun, 12 noon local time, the sun is on the observer's meridian, so it's as high up in the sky as it's going to be, and it's at its maximum altitude above the southern horizon. So this is for all observers north of the sun, so in the northern hemisphere, more or less. So when we talk about locations things are in the sky, the zenith is the point directly above your head. So it's always 90 degrees from the horizon. And the altitude is the height of an object measured up from the horizon. So when we talk about the altitude of the noon sun, that's the highest angle it gets to above the horizon. So you're measuring from looking out at the horizon up. And the zenith angle is the angle from the zenith down to the object. And that is always going to be 90 degrees minus the altitude. Because the altitude plus the zenith angle gets you to the zenith, and the zenith is 90 degrees from the horizon. So that's how you measure the location of something in the sky. We're mostly going to be talking about the sun. You can use the zenith angle of the sun and the date to figure out your latitude. So on June 21st, the sun is the highest in the sky. That's the summer solstice. The sun will be as far north as possible. It will be 23.5 degrees. The sun will be directly coming down on 23.5 degrees north. On this day, we measure the altitude to be 50 degrees. That means the zenith angle is 40 degrees. And our latitude will be our zenith angle plus the angle, the location of the sun. So the 40 degrees turns out to be the angle from where the sun is directly overhead to our current zenith. So to find your latitude, that will be 40 degrees plus 23.5 degrees, or 63.5 degrees north. Now, if you observe the sun to be at 50 degrees when you are at the equinox, you would be at 50 degrees north. That would be straightforward, because at the equinox, the sun is over the equator. It's at 0 degrees. So to find the latitude, you need to know two things. The zenith angle of the sun, which you can get by measuring the altitude of the sun, and where the sun is directly overhead, which is based on the date. Because that's, our calendar is based on the seasons. You can look that up. So latitude is going to be your zenith angle plus the number of degrees overhead the sun is in your hemisphere, or minus the number of degrees overhead the sun is in the other hemisphere. So it's the zenith angle. Your latitude will be the zenith angle plus or minus the sun degrees. And it's, if you're in the northern hemisphere and the sun is in the southern hemisphere, you will subtract. If you're in the northern hemisphere and the sun is in the northern hemisphere, you'll add. So here, for example, a ship's captain measures the noonday sun at an altitude of 30 degrees towards the south on December 22nd. Well, this ship's captain is looking south, so he's north of the sun. And it's December 22nd, so the sun is at 23.5 degrees south. So they're in opposite hemispheres. The zenith angle is 60 degrees because it's 90 degrees minus the altitude. So 60 degrees minus 23.5 degrees gives us 36.5 degrees north. That is the latitude of the ship. So in general, if you know what bay it is, and you can measure the altitude of the sun, which is honestly not that hard. It takes a protractor and a piece of string. Or you can measure the altitude of Polaris. That's another way you can do this. There's certain stars you can measure as well. You can figure out your latitude. Latitude is pretty easy to measure. So here, for example, 23.5 degrees here, 60 degrees from the sun to the zenith. And you have to subtract the 23.5 degrees to measure from 0 to the zenith angle, to the zenith. Okay? Now here, we have a ship's captain measures the noonday sun at an altitude of 70.5 degrees towards the north on December 22nd. What's the latitude of this ship? Well, on December 22nd, the noonday sun is over 23.5 degrees south. But here we're measuring 70.5, the altitude is 70.5 degrees towards the north. So we're in the southern hemisphere. So the zenith angle is going to be the complement of 70.5, 19.5 degrees. We're in the same hemisphere, so we will add the zenith angle and the degrees of the sun. So this will be 19.5 degrees plus 23.5 degrees. It'll be 43 degrees south. This ship is at 43 degrees south. The sun is very high in the sky. In the southern hemisphere at the northern hemisphere's winter solstice. Because, you know, that's the summer solstice for the southern hemisphere. Now, in theory, determining longitude should be easy because the sun travels westward at a steady degree rate of 15 degrees per hour. So if you know what time it is at the prime meridian, and you know what time it is locally, well, if you know what time it is at the prime meridian and it's local noon, then it's very easy to calculate what time the difference. So if the noonday sun at your position is observed at 2 p.m. Greenwich Mean Time, and then you know you're 2 sun hours west of Greenwich or 30 degrees west. So 15 degrees per hour times 2 hours is 30 degrees west. Now, interestingly, historically, latitude was much, much harder to measure. Because it turns out to do this, you need accurate clocks that will hold on to time for long, will remain steady and accurate for long periods of time. So this trick depends on, long-term stable clocks, something that took a long time to build, especially that will work on a ship that's rolling around. I mean, a mechanical clock with a pendulum on a rolling ship that messes things up. And so there was a long period of time, and it took a long time to figure out ways to determine longitude. Now the seasons. As the Earth revolves around the sun, its axis remains tilted at 23.5 degrees from the vertical. This constant tilt of the Earth causes the Earth's seasons. It turns out that both summer and winter occur when the Earth is at its furthest point from the sun and its closest point. And in fact, the sun is at its closest point in its orbit to the sun in January. So it's winter then. But it's summer in the southern hemisphere. So that is also why, in fact, sunscreen is more needed in the southern hemisphere than the northern hemisphere, because the southern hemisphere's summer is when the Earth is closer to the sun, so they get even more light and more exposure. So as the Earth revolves around the sun, we can designate 4 particular days that correspond to important times of the year. And these have been known about for, it's hard to know how long they've been known about. Literally tens of thousands of years. Like Stonehenge was set up to tie to these various dates. People built things tied to them all, probably as long as people have been people. People have known about these days. And we put important events at these days. And so, because the winter solstice is the shortest day of the year, the summer solstice is the longest day of the year. If you're towards one of the poles, at the equator, the light and dark hours are always the same. There's no variation in length of night and day, but the variation gets more and more extreme as you go further away from the equator. So here at the 4 seasons, at the summer solstice, which is June 21, 21st, or 22nd, the sun, the northern hemisphere is pointed towards the sun. At the vernal equinox, March 20th or 21st, half the Earth is illuminated. That's solstice is sun stopping. It reaches an extreme. Equinox is equal night. Day and night are the same length on the equinoxes. So June 21st or 22nd is the summer solstice. March 20th or 21st is the vernal equinox in spring. December 22nd or 23rd is the winter solstice. And September 22nd or 23rd is the autumnal equinox. And I did that backwards. Whatever. And we, of course, orbit, we go the other way around. And there are lots of holidays and stuff right around these events. For example, Christmas is on December 25th. That's because the 25th in the old Roman calendar was the solstice. Christmas is set at the winter solstice. There's been a bunch of modifications to the calendar. Things shifted around, so now it's a little bit off, but that's why it was there. Whole bunch of complicated theological math went into determining that. Based on a bunch of weird ideas about famous people being born and dying on the same day of the year. But the winter solstice is 23.5 degrees south. That's when the sun is over 23.5 degrees south. That's the Tropic of Capricorn. At the winter solstice, the sun is lower in the northern hemisphere. There are fewest days of hours of daylight. and the sunlight is less intense because the angle of the sun affects the intensity of the sunlight, which is the main reason it's colder. There's less light in the day, there's less hours of light, but the angle of the sun actually has a bigger impact. The vernal equinox is at 0 degrees. The sun is over the equator. That's spring. The summer solstice, 23.5 degrees north. The sun is over 23.5 degrees north. That's the furthest north it goes. The sun is higher in the northern hemisphere. You have more hours of daylight and more direct and more intense sunlight because of that. And at the autumnal equinox, you will once again, the sun is once again over the equator. At the equinoxes, you have equal length day and night. At the solstices, you have the longest and shortest days of the year. The sun's overhead position is never greater than 23.5 degrees latitude. And the sun's position will always be directly south at 12 noon local solar time for an observer anywhere in the conterminous US. And also Alaska, but not Hawaii. Hawaii is far enough south that you can actually get the sun directly overhead. The solstice is the furthest point of the sun for the equator. Solstice is sun standing still. So that's where it comes from. The summer solstice is the most northern position. The vertical noon sun is over 23.5 degrees north. The winter solstice is the point where the sun is the furthest south. The vertical noon sun is over 23.5 degrees south. So the sun's overhead position varies over a total of 47 degrees from 23.5 degrees north to 23.5 degrees south of the equator. When it's directly over the equator, both day and night are the same length all over the world, with two exceptions, which are the poles. The poles get 6 months of sun in the summer, local summer, and 6 months of dark in the local winter. But everywhere else at the equinox, you get equal day and night. The vernal equinox is March 21st or 20th, I think. And the autumnal equinox is September 22nd or 23rd. It shifts by a day because the length of the year is not perfectly an even number of days. So it's not always the same day. Now, because the sun is so far away from the earth, light from the sun, rays of light from the sun are effectively parallel. It's so far away that for all intents and purposes, all the light, while it is spreading outwards from the sun, it's so far away that all the light coming from the sun is basically parallel. So half of the Earth's surface gets illuminated, is daylight. The other half is dark. That is how night and day happen. Nighttime is just when we are in the shadow of the Earth. The number of daylight hours at any place on the Earth, however, depends on the latitude and the day of the year. Because the seasons, the fact that you get more sun in the summer and less sun in the winter is due to the fact the Earth is tilting. So the halves of the Earth that are illuminated don't pass through the poles. So here is a video showing how the seasons work from the point of view of the sun. This will look like the Earth is tilting. It's actually not changing its direction. It's just traveling around the sun, always pointing in the same direction. But, it's effectively illuminated from the other side 6 months later.
The axis of the Earth is an imaginary line on which the Earth rotates. It links up the two poles. Both the axis and the Earth are tilted at an angle of 23.5 degrees during a revolution. The tilting of the axis results in direct sunlight falling on different places during different seasons. This causes variations in the duration of days, nights, and seasons. Relationship between the location of the overhead sun and the seasons. Similarly, the revolution of the Earth and the tilting of the axis results in different angle of the sun during different periods. When the sun is directly overhead, we call this the overhead sun. At this time, the Earth's surface and the midday sun forms a 90-degree angle. Different locations of the overhead sun results in variations in the amount of solar radiation received in different areas and at different periods. Spring equinox. On the 21st or 22nd of March. The overhead sun is over the equator. The equator receives the largest amount of solar radiation. At this time, the northern hemisphere is in the spring equinox, while the southern hemisphere is in the autumn equinox. The angle of the sun decreases towards the poles. On this day, the two hemispheres receive a similar amount of solar radiation, and the length of day and night is the same at all places on the Earth. After this day, it is spring in the northern hemisphere, where the day is longer than the night. In the southern hemisphere, it becomes autumn, when the day is shorter than the night. Summer solstice. On the 21st or 22nd of June, the overhead sun is over the Tropic of Cancer. It receives the largest amount of solar radiation. At this time, the northern hemisphere is in the summer solstice, while the southern hemisphere is in the winter solstice. The angle of the sun decreases towards the poles. On this day, the length of daytime of the northern hemisphere is the longest in the year, while that of the southern hemisphere is the shortest in the year. Besides, there are 24 hours of daylight at the Arctic Circle and 24 hours of darkness at the Antarctic Circle. Autumn equinox. On the 22nd or 23rd of September, the overhead sun is over the equator again. The equator receives the largest amount of solar radiation. On this day, the northern hemisphere is in the autumn equinox, while the southern hemisphere is in the spring equinox. The angle of the sun decreases towards the poles. On this day, the two hemispheres receive a similar amount of solar radiation, and the length of day and night is the same at all places on the Earth. After this day, it is autumn in the northern hemisphere, where the day is shorter than the night. In the southern hemisphere, it becomes spring, when the day is longer than the night. Winter solstice. On the 21st and 22nd of December, the overhead sun is over the Tropic of Capricorn. It receives the largest amount of solar radiation. On this day, the northern hemisphere is in the winter solstice, while the southern hemisphere is in the summer solstice. The angle of the sun decreases towards the poles. On this day, the length of daytime in the northern hemisphere is the shortest in the year, while that of the southern hemisphere is the longest in the year. There are 24 hours of darkness at the Arctic Circle and 24 hours of daylight at the Antarctic Circle.
So, talk about the circle of illumination. It's the half of the Earth that's lit up. So here is the circle of illumination on one of the equinoxes. The Arctic circle is at 66.5 degrees north. The Antarctic circle is at 66.5 degrees south. The tropics are here. Half the day, half the Earth is lit up. And that line passes through the poles. So night and day are of equal length. So here you can see at the northern hemisphere's summer solstice, you can see how, while half the Earth is still lit up, more of the northern hemisphere is lit up than the southern hemisphere. The days are longer in the northern hemisphere and shorter in the southern hemisphere. And in the Antarctic circle, and above it, you'll have 24 hours of daylight. So, another thing the Earth does is it turns out, well, I said the Earth always points in the same direction. Similar to a top, it will wobble. The direction will slowly change over time. So, if you've ever spun a top, you've seen that it wobbles. This process of wobbling is called precession. It has to do with combining of torques. The same thing happens to the Earth as it rotates. It slowly precesses in a clockwise direction over a very long period of time. And this doesn't affect the seasons we observe. In fact, our calendar is based around the seasons. So over hundreds of years, where we are in the Earth's orbit at any date will change. This is actually why zodiac signs have changed over time. So the Earth slowly precesses in a clockwise direction. The period of this precession is 25,800 years. And interestingly enough, this was figured out in a couple hundred BC. Like ancient Greeks worked this out. It would take 2,800 years for the Earth axis to precess, 25,800 years for the Earth's axis to precess through 360 degrees. And the reason you can tell this is because the star that the Earth's axis points at changes over time. So right now it's pointing at Polaris, but over time that will change. And by looking at hundreds of years of astronomical data, it's possible to figure this out and calculate this precession. So as the Earth precesses, Polaris will no longer be the North Star. Eventually it will be Vega. Now, the precession of the Earth's axis has little influence on the seasons because the tilt of the Earth with respect to the sun remains constant. However, the Earth's precession will slowly change the stars that can be seen in each hemisphere and season. This is why your zodiac signs, the zodiac signs have actually changed over the centuries. So the Earth is wobbling.
The Earth's axis points at the North Star, and the heavens have been revolving around that star since the dawn of time. Except they haven't. When the Egyptians built the pyramids, the North Star wasn't our current North Star, Polaris. No, it was Thuban. Why did it change? It's because the Earth's axis is moving. This motion was first discovered by Hipparchus. He was looking at the positions of the stars and comparing them with their positions a century earlier at the same time of year. He found that the stars were moving at least 1 degree every century. What could be causing this motion? When you're riding a car and the car turns, you feel an acceleration. In the same way that you experience an acceleration when a car turns, there is also an acceleration as the world turns.
This acceleration works against the force of gravity, so you actually weigh less at the equator.
And you weigh more when you're at the North Pole, 1% more.
This also causes the Earth to bulge. The Earth is 26 miles wider at the equator.
Because the Earth is not a perfect sphere, the gravitational force of the Sun isn't perfectly balanced. One side of the Earth gets tugged just a little bit more, and this causes the Earth's axis to spin, completing one revolution every 26,000 years. This also affects the length of the year. Now, you can measure the length of a year several different ways. One way is to look at the seasons. This is called the tropical year. Another way is to look at the positions of the stars. This is called the sidereal year. In January, the sun is in the constellation Capricorn, which means children born in January have Capricorn as their astrological sign. Over the course of a year, the sun moves through all the signs of the zodiac. Once the Earth is back in its original location, we have completed one sidereal year. But the tropical year doesn't depend on the Earth's position. It depends on the Earth's axis. When the North Pole faces away from the sun, we in the northern hemisphere experience the winter solstice, the shortest day of the year. If you measure the length of time between two winter solstices, you get a tropical year. So, what's different? Well, if the Earth's axis is moving, it could line up with the sun before the Earth has returned to its original location. This is what happens. Although the effect is small, the axis only moves about 1/100th of a degree, and a tropical year is only 20 minutes shorter than a sidereal year. How did this affect the development of the calendar? Let's go back to the Romans. You may remember Julius Caesar as the man who conquered the Gauls, overthrew the Roman Republic, and named the month of July after himself. But in his free time, he cleaned up the Roman calendar, which was a total mess. Before Caesar, the calendar lasted between 355 days and 378 days. Caesar put it at 365 days, with a leap day every 4 years. This was the Western calendar, until Pope Gregory XIII said, "That's not good enough." He removed some of the leap days to better match the length of a tropical year. The Gregorian calendar wasn't adopted in Russia until 1918, and as a result, the Russians showed up at the 1908 Olympics 12 days late. Why did Pope Gregory base our calendar off the tropical year? What if he had used the sidereal year?
Imagine it's the year 15,000 AD.
And Americans are celebrating Christmas in the middle of summer. And that is what a sidereal calendar would mean. Now, a tropical calendar gets the seasons right, but it puts the Earth on the opposite side of the Sun
in the year 15,000.
And so, Geminis will be born in December, Cancers in January, Leos in February, Virgos in March. Everything will be backwards.
And as we know from astrology, the position of the sun and planets at the moment you were born predicts all future events in your life. Here's a chart showing you the positions of the planets when I was born. As you can see, I am destined for greatness. Don't believe me? Just look at my horoscope today.
Today, you will make a YouTube video. Some people will think that you love astrology, while others will think you're being sarcastic. But everyone will love your video. For more astronomical videos, please click to subscribe.
So, over about 25,800 years, the Earth will precess completely. So, the pole star in 2000 CE is Polaris. In 1400 CE, it will be Vega as things move. And the reason the year is based off a tropical year, more accurately based off a tropical year, is because one, it fits our seasons better, but also the Gregorian calendar was designed to better calculate what Easter is, and Easter is based off relationships with the solstices and equinoxes and stuff. So that means, well, there was drift, so they were fixing the drift, but it was just to be more accurate to the tropical year to better match the seasons. So that's the end of chapter 15. So another name for the parallel lines on the Earth's grid system are lines of latitude, like a ladder. They go up and down, north and south. The meridian lines of the Earth's grid system are lines of longitude. These go along, east and west. The lines of these that are equidistant from each other are the parallel lines, the lines of latitude. The meridian lines all meet at the poles. All the meridians intersect at the poles. And they get closer together the further north or south you go. The maximum value of the parallels is 90 degrees north or south. The maximum value of the meridians is 180 degrees east or west. Lines of latitude are measured north and south of the equator. Lines of longitude are measured east and west of the prime meridian. The approximate latitude and longitude of Spain, looking at this map, well, Spain is here. Latitude, about 40 degrees north. Longitude, it's a little bit west of the prime meridian, so maybe a few degrees west, like 2 or 3, maybe 5, because this is 20 degrees, half of that, maybe somewhere between 0 and 5 degrees west. What type of map keeps latitude and longitude lines parallel, but in doing so it distorts landmass sides? That's a Mercator projection. The type of map that shows the features of the ocean floor is a bathymetric map. The type of map that shows land elevations is a topographic map. Or a contour map is a way you can draw a topographic map. The type of map that attempts to remove landmass size distortion is the Peters projection. There are a whole bunch of other projections out there, but those are 2 of the most common ones. The type of map that shows the types of rocks found in an area is a geological map. The difference in altitude between 2 contour lines is called the contour index. Tightly packed contour lines tell you that the altitude or the height is changing quickly, so the area has a steep slope. Widely spaced contour lines tells you that the height is changing slowly, so the area has a gradual slope. Hatcher lines on a contour map indicate which way is down. The little hatches point down slope. Gradient indicates the steepness of a slope. The gradient is determined by taking the change in height over a distance and dividing it by the distance. So the change in altitude over the distance. Which is longer, the sidereal day or the solar day. The solar day is slightly longer by about 4 minutes. How many degrees does the Earth complete in its orbit around the sun in one day? A little bit less than 1. How many time zones are there? 24. Same number of hours in a day. How many degrees of longitude separate each time zone? 15 degrees. 360 degrees divided by 24 hours. If you travel west, when you travel west, the time will go to an earlier time. So you will gain an hour of time. You travel east, the time will go to a later time, so you will lose an hour of time. The prime meridian is located at 0 degrees longitude, while the international dateline is located at 180 degrees longitude. The latitude line located at 23.5 degrees north is called the Tropic of Cancer. The latitude located at 23.5 degrees south is called the Tropic of Capricorn. To calculate your zenith angle, you would subtract the altitude angle from 90 degrees. To calculate your longitude from the sun position data, you multiply the number of hours of difference for the noonday sun from GMT time by 15 degrees. And seasons on Earth are due to the tilt of the Earth's axis. When the direct rays of the sun reach 23.5 degrees north or south, the days these occur on are referred to as the summer and winter solstices. When the direct rays of the sun are at the equator, the days these occur on are referred to as the vernal and autumnal equinoxes. Solstice is sun still, it's when the sun changes direction, so it stops moving up or down. Equinox is equal night. Day and night are equal in length. Due to the circulation, the circle of illumination, the poles have 6 months each of day and night. The Earth's axis actually moves in a predictable pattern every roughly 26,000 years. This is referred to as the precession of the Earth's axis. And that is all. That is chapter 15. So that's it for today. The chapter 15 homework will be due on the 14th. That's after spring break. The chapter 15 quiz will be online. It will be the week after spring break from the 11th through the 18th. And the test grades will be posted up to Blackboard later today. I'm saying by tonight, but everything is graded. I got the scores up. I just need to put them on Blackboard. And if you want to look at your tests or quizzes, you could drop by my office hours because I have them all in my office. But that is all for today. Have a nice day. Have a good spring break, everyone. Do not come here next week. No one will be here. Have a good break.
Mr. Kearling?
I believe you still have SI this week.